recording, and you can
yeah, thanks again for organizing this very nice workshop. Good. So here a very brief reminder where we shall continue. So we started out in the first lecture in a very algebraic spirit, analyzing slightly sort of the formalism of VOAs, applying it to the Virasoro VOA and its unitary representations, which were denoted by H alpha 1. So for it to be unitary, we assume that the parameters alpha are of a somewhat funny form, and conformal dimensions, also maybe this as a quick reminder, are parameterized in this way, which has become somewhat traditional in the literature. Good. So then the main gadget, the main player in the game, were so-called intertwining operators, which intertwine between different representations of the Virasoro algebra. Again, we are restricting to unitary ones, but basically all I'm saying permits analytic continuation in these representation labels. And these intertwining operators, well, they have an additional argument which eats vectors from a third representation, H alpha 2, and they're defined by a collection of somewhat awkward looking relations like that. So this is can be read, so this is here a special case Y, where we insert here the highest weight vector. For that case, we have the relations of this form, where basically taking commutator with LNs, roughly speaking, we're getting a differential operator describing some infinitesimal action of elements of the loop group. And then there's a second one which tells us how to remove additional Virasoro generators, creation operators from the argument, from the, say, second argument of these intertwining operators. I've wrote a full expression, but sort of the way to think about it is like that. So what one gets here is something where you have ordered in a suitable way the Virasoro generators to the left and to the right, depending on whether you're talking about positive or negative modes. Okay, then we introduced this as a diagrammatic notation, but this was just a convenient diagrammatics, and we considered then compositions of these y's, so something like y times y would have this diagrammatic notation, and another one would have this diagrammatic notation for 1 over 2, so let me reproduce the values here. For 4. And sort of one of the main results that we announced with, or that was announced in Chin's talk then, is that by now we rigorously know that there are integral transformations of this form here. So I want here to use some graphic letters. No, sorry. This is the fusion kernel, sorry, myself, delta, for which we saw the explicit expression in Chin's talk. And this here is to be understood as a linear relation between two bases in what we are recognizing as the space of conformal blocks of the unitary principal series of Virasoro representations. So this was sort of the most important statement that was made last time, where we basically ended the talk after discussion of analytic properties of all that. So again, all this was very algebraic in spirit, and now we're entering part 2 of the lectures, which basically exhibits geometric background, which has a lot to do with this theory of Riemann surfaces. And as a starting point, I mean, to make the link, to make the translation, we start with a few simple observations. oops, we introduce so-called block function, which now is function on threefold tensor product of representations to C, a linear functional on tensor products of representations, which is going to be defined in terms of what we know with these vertex operators, B alpha for W3, whoops. So it eats something in this triple tensor product, and we're going to define it. This expression. So we're using these vertex operators to define this form, this linear form, like so. So this here is the Shapovalov form that we introduced in order to take matrix elements, and this is taken here in H alpha 3. Okay, so that's the definition. And now comes sort of the main claim, which sort of brings us into the world of geometry and Riemann surfaces, which can be formulated as follows. The lemma, although will require a little bit of work to fully prove it, but again, I hope that it will be clear that it's essentially elementary what you need to do, even though perhaps depending on how you approach it, it can be slightly tedious. So here comes a Riemann surface, and okay, you may of course have guessed or know already what this is. It will correspond just to the idea that we take here our diagram and thicken it with something that looks like a three-hole sphere, well, which of course by conformal transformations is identified with the three punctured sphere, where here we have a distinguished point identified with Z, referring to the standard coordinate on the Riemann sphere provided by its relation to the complex plane. And point 0 somewhere here, so we have a somewhat special position of the marked points, which we can always assume without loss of generality. Okay, so here comes the statement. Any given vector fields, well, I could just speak of functions, but sort of for the more geometric picture, it will be useful to think of vector fields in order to understand here also some global properties. So we introduce here coordinates yi in the vicinity of the puncture. So Z1 is 0, Z2 is Z, Z3 is infinity in my notations, and then we're introducing coordinates around these punctures here in some little disks. So here we have a coordinate y2 in this disk, and these coordinates are supposed to vanish at these points just for convenience and for the following statement, namely what we can then introduce is Ti of eta. It will be a linear combination of Virasoro generators obtained by taking this vector field and integrating this around here with a small circle. Say this would be here gamma 2. Small circle around this marked point, and that's what we integrate along. And then we have et of z, t of z, z. Take here coordinates. That's what right? So that's what I introduce. It's just a definition. I should introduce the notation T of Z is sum over Z to the minus n minus 2 ln. Minus infinity to infinity. Okay, yes, now comes the statement. So these were just definitions of eta for any vector W. This is annihilated with all W in H alpha, which is shorthand for here, H alpha 3. And for all eta of the type above, this here is simply defined as T3 of eta tensor 1 tensor 1 plus 1 tensor T2 of eta. So simply we're adding up the actions that are defined by this formula here associated to the three different functions. Plus 1 tensor T of eta T1 of eta. So that's the statement, okay, which we perhaps have to digest for a second if you have not seen it before. It says that the gadget that we have defined here, which is a form on triple tensor products, has a characteristic invariance property with respect to a natural action of the Virasoro algebra, which is just coming by the theory of complex functions on that Riemann surface, because we're using, well, vector fields on the three-punctured sphere in order to define the action on the triple tensor product. That's the whole basis for that definition. And my claim is simply going to be, well, okay, too bad. I'm just erasing what I now want to refer to. Okay, still here, I was referring to these properties star and double star in the definition of this intertwining operator calligraphic Y. And my claim is that the proof basically is to establish the equivalence between this invariance property. Maybe give it a name here, call it CWI for conformal Watt identity. So this defining invariance property, I claim, is equivalent to star and double star that were called schematically here at the beginning. So basically is CWI is basically equivalent to star. This is checked by elementary computations. You just need to pick sort of a suitable basis for the vector space of vector fields on the three-punctured sphere, and then show that by choosing them in a clever way, you can recover basically star and double star as particular consequences of what we call here CWI for Watt identity. Good. So this basically is the first step in the translation between algebra and Riemann surfaces. It basically says that the algebraic relations, which were defining the intertwining operators Y, can be equivalently rephrased in terms of some set of conditions for invariance of a linear functional on triple tensor products, which is coming from the geometry of the three-punctured sphere. Therefore, yes, the three-punctured sphere is naturally sort of the geometric like background for understanding these intertwining operators Y. Good. So I already changed the diagrammatic notation somewhat in order to get the Riemann surface into the game and to make them visible. And now what we want to do is to note that composition of the vertex operators, as we studied, has to do with considering more complicated Riemann surfaces, which you can obtain by gluing the simple ones that we started from, the three-punctured spheres. So we start with a bit of like geometric preparation. which is, we'll talk about how to glue, well, to begin with spheres, but then we can basically take the same definition almost and apply it recursively in order to get more and more complicated surfaces. So here comes the picture that you probably find in many references. So we have here Riemann surface C2 with a marked point P2. And we have another Riemann surface C1 with a marked point P1, around which I emphasized it is important that we choose local coordinates around our marked points. So let's do that. So let's assume maybe that this, with respect to the suitable coordinate, which we denote by Y2, is the unit disk that isn't really central. I can always assume this without loss of generality. Likewise here in the disk we have a coordinate Y1, and maybe here we have some generic point Q2, which we want to describe a rule which allows us to identify point Q2 with another partner point Q1 on the other Riemann surface in such a way that then by identifying these disks, we are sort of fusing or gluing together these two Riemann surfaces. So how's this done concretely? Well, maybe I'll write the equation here to have it better visible. I want to impose this type of equivalence relation, identifying points in order to get a new Riemann surface, which is supposed to hold if and only if the coordinate value associated to point Q2 when multiplied with the coordinate value associated to point Q1 is a fixed parameter. Here we just introduce a parameter which we keep fixed once and for all, which basically labels this particular type of gluing. Well, you can then find sort of that this works well in disks, in annuli around the puncture, because yeah, if you shrink here Y2 to 0, it would amount to having Y1 to infinity. So this here is basically defined by the image of the outer boundary here on the second surface under this gluing identification. So these annuli are thereby getting identified with each other. So the resulting picture will look something like so, where we see here embedded some annulus, which is the image here. Maybe we can call it here annulus. So then we find it here again embedded into the glued surface. And maybe sometimes, well, you can, if you wish, indicate the necessary things. So this C here could be denoted as follows. We are gluing with a parameter Q and marked points P2, P1, like so. Good, so that's basically the standard or a relatively standard definition of how to glue two Riemann surfaces, which probably many of you have seen already before. Let me also note what this parameter Q does is it gives basically the size, let me not be very precise here, these annulus, roughly speaking, so if you can think of the length corresponding to log Q. Well, no, I should rather say sort of the radius of the circle you should identify with. No, it's qualitatively right.
This is what people call plumbing, right?
That's what people call plumbing. Yeah. Good. So we have introduced the geometric gluing operation on the level of Riemann surfaces. whole point now will, of course, be to point out, and I'll have to be sketchy here, how this is lifted to the level of conformal blocks. So next step is to talk about doing blocks. We assume the setup up here, let me not repeat anything. So then we want to introduce, we assume given a conformal block here on, well, this can be disjoint union, or it can be two punctures on one and the same Riemann surface. Both possibilities can be considered. So given a conformal block, here's my notation. C2 cross C1, say for the first case that we have a disjoint union of two surfaces. And I had introduced here some tuple alpha, which here now is going to be more general. Will run, say, from alpha n to alpha 1, the number of punctures. So much. So here in this tuple, we consider maybe the two, consider the special cases where two of them, which I can, without loss of generality, assume to be like neighbors in my numbering, they have the same value. That is a restriction I need to make. And what is this? This is something from H alpha n. Oh, okay, sorry. I skipped something, and but let me finish this and make sort of what I skipped into a little box here. Something very important. First, want to say what conformal blocks are, what the definition is. More generally, if I have a Riemann surface C, so what generalizes these invariance conditions CWI? Well, here it is. So I thereby introduce notations of C tensor product maybe up to n R. It's numbers. This tuple notation is this here. And these are linear maps. Satisfying the alpha T of eta W 0 for all vector fields eta and C. Here comes the most important adjective, holomorphic. And if I say they're holomorphic on C, as C was here now going to be Riemann surface of genus G, that is N, G handles and N punctures. When I say holomorphic, I do allow that there are singular, that is meromorphic, have poles at the punctures. So they're holomorphic away from the punctures, which is the same as saying that they're holomorphic on C. Well, plus conditions about I don't want bad behavior. What's it? I could just say meromorphic. Right. Thanks. I don't want them to be meromorphic on C, because that would allow poles also elsewhere.
No, but one of these poles at the margin.
Only at the margin. That's only. and for all W H alpha. So that is sort of the straightforward natural generalization of what I called CWI, the conformal Ward identities, which are perhaps the most crucial, say, condition with respect to Virasoro algebra that conformal blocks need to satisfy. Good. Having done this and having introduced the necessary notations, now we want to describe their gluing. Yeah.
The gluing of surfaces almost doesn't depend on the choice of coordinates.
A lot upward. A lot. So
there should be also.
There is a story, okay, which I don't really want to go much into about sort of how to change coordinates, what kind of coordinates.
A particular Q can be absorbed into one coordinate.
The Q could be absorbed in a redefinition of one of these two coordinates. We just choose to keep it explicit in order to have a tunable parameter that at some point turned out will no longer be absorbable into the coordinates. So, but yes, there is some.
And the gluing in the corresponding maps on blocks will also depend on this code.
So what we're defining here, and this is also clear here, right, is our objects that define not only on the choice of complex structure, I will say a little more about this in a moment, but also on a collection of choices of coordinates around the punctures. Because this is what is used in order to define these objects, because we're defining them by Laurent series with respect to specific coordinates, etc., etc. So a priori here, this is something that is defined.
Conditionality is really mild, right? It's just vanishing at the points. So with undercoding change, it should not really.
Well, you know, let me for now just stress the coordinate dependence is there, and for some aspects, it turns out to be pretty inessential, but there is a residual aspect where it will be extremely important. So,
I mean, because the first thing that you define is on the actual Riemann sphere. When you do this sewing, you have some uniformizing function. You no longer have the Riemann sphere. So from our point of view, just for like, you know, vertex operators, this is huge because you only have the, so I don't understand because you know, your first, when you're just on the Riemann sphere, you have this correspondence, but that's just for the actually already uniformized Riemann sphere. When I do this gluing, I have this barbell now or something. This is not the Riemann sphere. So even if I put in like the vacuum over here or something, I would still have a uniformizing function to get back to the Riemann sphere. And this involves extreme coordinate changes, okay. No?
Well, thank you. Thank you for this question or for this remark. So, in discussing the Riemann sphere, I was choosing very special coordinates because on the Riemann sphere, I'm having the luxury of having very natural ones coming from the complex coordinate on the complex plane. I was using them to write down the definition. What we may observe at this point, I didn't want to spend much time on this. What we may observe at this point is that these definitions that we wrote, both of the gluing as well as these conformal Ward identities, make sense for much more general setups, much more general choices of coordinates. In the end of the day, what I want to propose is it is useful to consider the choices of coordinates that are coming from the Riemann sphere for a specific setup, a specific set of coordinates that we can use for gluing more general Riemann surfaces. Having in the back of my mind that all this does permit, and for this, well, Collin and collaborators have set up a very nice formalism, but it's also elsewhere in the literature. You can then also operate with much more general choices of coordinates. But we are allowed to consistently use coordinates coming from the Riemann sphere and doing just Riemann spheres. This at least gives a definition of a collection of conformal blocks around the boundary of the moduli of complex structures corresponding to these Deligne-Mumford nodal degenerations.
what was the last part that?
There's, okay.
I'm sorry.
We come back to this. So there is the, you know, what we can see here from the picture is that there is the limit where Q goes to 0. In that limit, this annulus shrinks to just a double point. It gives a nodal surface. And this nodal surface represents what is called a boundary component in the Riemann-Mumford boundary to the moduli of complex structures on the Riemann surface. But I'm jumping a bit ahead of myself here. That's what I meant. Okay. Christoph had a question, I think.
No, I wanted to ask Alexei's question in different terms. In the rational case, we are used to the equivalence of a topological modular functor and complex analytic modular functor. Are you insisting in your parameter Q because you do not expect such an equivalence for Liouville theory?
Okay. I mean, what you're asking about is meant to be part 3 of my lectures. That is maybe that's the quickest way of handling this question for now, because I do want to discuss related matters ultimately. But for now, you know, okay, it's more the Virasoro versus Riemann surface aspect that I'm discussing here. And yes, there was one more.
I guess there should be also one identities which correspond to change the modular parameters of the Riemann surface.
Coming. I'm not, you know, one step after the other. Oh, okay, so good. I mean, this is perhaps slightly boring, but I need to write it anyway. So assume, okay, I want to rename here to beta for the this is what is given, and I single out here notation particular factors in this tensor product. And we want then produce something, let's call it C21 of Q. So now I'm stressing here, it depends, it's a family of such Riemann surfaces depending on this parameter Q, about which more needs to be said. But not now. And this is what it is H alpha n tensor. And here, these factors are just to be omitted, right? Deleting them from the list of tensor factors here. And that's a map. Again. And the rule, and here I have to be, well, extremely quick and schematic. There's what that could and should be said about it. So what we need to define are the values on a basis for that tensor product space. And for these, okay, here is some notations that is going to be introduced. And what we're going to do is simply take here in the factors, which are singled out here, the basis and the dual basis with respect to Shapovalov form. And we weight this with a Q to the L0. Like so. Oh, this I call check. And these are U and some index set. You check. You take the same index set. These are dual bases here with respect to H alpha, meaning that I want V alpha, ups be nu. Oh, this was better, sorry. check. It's also from delta. Okay, that's the definition. Now you're going to ask me why do you make this definition? Well, the reason, and this is again a lemma or proposition, is that with this definition and due to this property, the defining invariance property of the Shapovalov form, this guy will satisfy our conformal word identities, like here, if this guy did it originally. That is, of course, exercise. Maybe not quite so trivial, but doable. Also not like.
I have a question. How do you know the series is converging?
Come on, we discussed this on Friday, right? So, and this is not convergent as yet. It is formal, and it is thanks to the results that you guys are proving that we know it's convergent.
Is there a generic?
Okay, that's we discussed this already.
No, but the question is there a generic argument for this? Or is there an argument that is general, or is it model dependent?
For
convergence of the series.
No, the state of the art is what you are proving.
No, but in general,
That's
I mean,
my
take
answer.
H3 or H3 based on Newton or whatever that has continuous spectrum. Is there a generic expected argument or?
Okay, it was of course previously, at the level of theorems, no, but there have been several like partial results for special cases or evidence. For example, there's some argument, I believe, for four-punctured sphere H3 you were mentioning, thanks to Knizhnik-Zomlochikov, where with some estimates you could prove convergence, I think, for H3 four-punctured sphere. So it is a little better perhaps than nothing. But yeah, I mean, okay, for now, I didn't want to re-enter this discussion because for this I would like to refer to you. But for now, it's a formal series, and the hope originally and now theorem is actually convergent. That's very nice. Let's stress this. Let's emphasize this. It's very important for the foundations of what I'm presenting. Okay, good. We have the gluing. Okay, let's see. And having defined the gluing, we end up having our families of conformal blocks. And let's introduce convenient labeling systems for that. So let's do it an example maybe of a genus 2 surface, maybe even without puncture. Of course, install punctures if you like. So here we have cutting curves, gamma 1, gamma 2, gamma 3. And you see with the naked eye, if you cut along these curves, you decompose it into two pairs of pans. We associate to each of them a gluing parameter, Q1, Q2, Q3. And it turns out to keep track of precisely how you glue, in particular also basically logs of the coordinates. It's useful to also introduce a three-valent graph, which we call gamma. So if you do it very carefully, you will simply observe that it makes a difference whether you cut open here, rotate by 2 pi, and reglue. Just noting the cutting curve would not recognize the difference. This graph will recognize the difference because it will be wound around the handle here one time. And it turns out that indeed conformal blocks care about this difference because yeah, it's related by some phases corresponding to what is called the Dean twists, but that are details which aren't necessary. I just want to emphasize, in general, we need not only the Tan's decomposition, but also this graph in order to have data labeling gluings unambiguously. Good, so here, notations, if we need them, we introduce, say, gamma as the collection of these cutting curves, and then say something that we call sigma, we could call it gluing pattern, which is this graph, like this, the little gamma, the capital gamma together. These are the data that we want. Okay, so quick remark. What mathematicians could call conformal blocks are these machines which eat up, which eat vectors and tensor products and spit out numbers. What physicists call conformal blocks are functions of sort. So how are they related? Well, the relation is simple. So that's part of this remark I'm making here. We can define functions which then depend on the collection of gluing parameters. So that's the tuple of all possible Q's that we have introduced into the game by simply taking here our block and evaluating a product of highest weight vectors. I don't know, I find the use of terminology here in physics math literature slightly unsatisfactory. This is sort of what physicists call conformal blocks. And this is what mathematician calls conformal block. We could avoid sort of confusion, call it chiral partition function also. Okay. But it's just, you know, it turns out that basically these functions can be used to reconstruct these guys. So therefore, if I understand fully their dependence with respect to the parameters Q, in essence, thanks to the conformal word identities, I can reconstruct these guys. But that is a somewhat non-trivial statement. In any case, I want to motivate that we can restrict attention to these functions that physicists call conformal blocks. Well, B, and here I'm finally addressing the question. No, not yet. Not quite yet, but I'm preparing for it. What is, for the following, I shall consider it convenient just to allow one functor. Otherwise, I would have to set up more sophisticated notations. And I can introduce something sometimes physicists would denote like this: expectation value of energy momentum tensor, or I shall abbreviate it. It's a function which depends on the conformal block and actually characterizes it. I shall also use this notation. So just to record the function, well, quote, quote, I shall be more precise about it in a second, on the Riemann surface that is defined in this way, where I take what? I take here the action of the energy momentum tensor on the highest weight vector. So again, here this was just by generating function of sort generators that we introduced before. And okay, I'm going to normalize it by its chiral partition function itself. That's an important object because in some sense, what I can prove is that provides an alternative characterization of the information that is informed. So one way of making this remark I made it a bit more precise is that this object and Whitson and analytic to C one. If the conformal block is coming from satisfies conformal block identities. In this statement, one direction is easy. Namely, well, yeah, one direction is easy, one direction is hard. Actually, I'm not sure. This is a bit more of a side remark, so I wonder how much of time I should spend on it. But yeah, I want to stress that this thing here basically characterizes the conformal block in this way. And we rather maybe go on to now comment on the complex structure dependence, which was implicit already on the way. So, okay, as these are meant to be introductory, semi-pedagogical lectures, let us recall what defines a complex structure is the atlas of complex coordinates on C. Now you may notice if I restrict attention to having coordinates in the gluing which are coming from coordinates on the spheres which are natural, if then I'm using the coordinates on the sphere, which are basically the standard ones in order to define coordinates around the punctures, then if you remember the gluing construction, how it went, we'll see it basically introduces an atlas for free, because on each of these spheres we have coordinates, and furthermore this crucial relation here, y1 of q1, y2 of q2 equals q, well, this is nothing but the change of coordinates between, say, local coordinates around the punctures from one side to the other. So this is clearly holomorphic, right? It says like y1 coordinate is q over y2 coordinate. So away from the locus where y2 vanishes, this is clearly holomorphic. So the key property in the definition here of a atlas of complex coordinates is satisfied, namely that the transition functions are all holomorphic. So such an atlas of complex coordinates defines the complex structures, and then we're forming equivalence classes with respect to holomorphic changes of coordinates in order to define what is called a complex structure, that is such an equivalence class. Good. All right, yeah, finally, I want to say something about variation of complex structure, as this was asked. I have 10 more minutes. Where do I want to do it? Oh, I take this space. Maybe I should call it definition theorem. I will explain what is definition, what is theory. For each okay, what I should say that requires a little bit of discussion is, of course, that the parameters Q here, they are parameters for the gluing construction, and that is a little bit of mathematical work. We can show the parameters Q that are introduced in this gluing construction, they form a set of coordinates, the so-called Plumding coordinates for, well, open subsets in the moduli space of Riemann surfaces. So Q moduli parameters or coordinates for the moduli of Riemann surfaces. And therefore, derivatives with respect to Q can be identified with the variations, infinitesimal variations of complex structures, or in other words, elements of the Teichmüller space, which is the space of deformations of complex structures. A bit of a cartoon to introduce notations, gamma, P, and all this is side of C.
Sorry, what is D?
So that's the statement which says, okay.
What is DP?
What is
DP?
Eta is defined on some.
Yeah, DP is the disk around the puncture here that we is equipped with a coordinate. So there's a coordinate here. Let's say y of q is associated. Here is a point q, and it maps y for the y of q in this disk. Okay, so what does it say? Recall, well, this here was nothing but the expectation value of q of y, which in turn was basically defined like this. So it says that the variation of a conformal block with respect to a variation of the complex structure is represented by the energy momentum tensor. I mean, now you know what it's something familiar to those who know CFT in this way. I mean, so that is an equation or a differential equation which tells me basically how the conformal blocks vary infinitesimally with respect to variations of the complex structure. And strictly speaking, from the point of view that I was presenting here, it is partly a definition because we were up to now defining conformal blocks for fixed Riemann surfaces. And there wasn't anything telling us how we could vary the complex structure. And the statement basically here is, this is sort of the only natural definition that we can adopt based on, say, the, well, theory of Riemann surfaces, because, and what is behind here, and here I have to be super brief, let me just mention it. What is behind here is that for each variation of the complex structure, I can find a vector field in an annulus surrounding the puncture, which corresponds to it. So for those who know, I mean, this is the statement, which I just may leave as is for now, but for those who know about it, what is behind is the so-called Virasoro uniformization theorem, which establishes this possibility to represent tangent vectors of the moduli of curves by vector fields on some annulus around an arbitrary point on the surface.
So P is arbitrary.
P is arbitrary, we can choose it. I mean, it was part of the data we had chosen in order to define our conformal blocks.
So it's the point around which you have glued your blocks, or?
In this case, right, so we had here defined conformal blocks. The defining word identities were formulated with respect to the choice of a point with a coordinate around it. So this was defining this gadget here. And this was what was defining our energy momentum tensor expectation value. So all this enters here. So therefore, all this here is with respect to a specific choice of P and coordinate around it. Okay, I mean, well, here, admittedly, providing the necessary background and digesting even the statement in full detail takes more time. I will invite you to just take it a bit schematic for now, as basically being a very natural way that this formalism provides in order to define how to vary the conformal blocks over the moduli space.
I think this should be arbitrary. It should be dual.
No, there is a very specific relationship between these two guys, right? And this is what is provided by so-called Virasoro uniformization theorem, which says something like the schematic titular space, that is the tangent space to the moduli, can be represented as a double quotient. So it's the vector fields on the annulus around P over the vector fields in the disk around P modulo whatever extends to the Riemann surface.
In some ways, it should be dual to the quadratic holomorphic
I
quadratic
don't
form.
need this here. I don't need this, but of course, in another way of formulating it, we would need what you refer to. But here we just need this: the mapping between tangent vectors and vector fields that is provided by the Virasoro uniformization. We can formulate it as we say here. Good. It's an important fact, and yeah, really, I wonder if I could end with this fact. Yeah, probably I should, and then next time I go to examples and do this modular functor type of story. Let me write the equation, say a few words, and then stop. Okay. The point is, I simply want to stress, which at some point becomes super important. Again, the coordinate dependence and how it is now manifested with respect to these expectation values. Sorry, just upstairs here, my notations. Do I have it? Sorry. No. Okay. If this is another coordinate, then there is a I want to describe how these functions, locally defined, of course, change under changes of the local coordinates on the Riemann surface. Namely, here's the formula y prime w squared c of y of w, and sort of the all-important extra bit c over 12 y comma w, which is defined as follows. The expression is not very illuminating, but we'll need it for something next time. These are the primes are derivative with respect to the arguments, so I'm considering here functions y of w and taking derivatives with respect to w denoted by prime. And okay, what else? This could be. So that is if there was not this term, I would say these transform just like quadratic differentials or some simple geometric objects. But yeah, with this extra term, this defines something that is called projective connection in math. And well, that's as it is. We will see that in particular here, these functions that physicists like to call conformal blocks, I was stressing over and over again, they do depend also on the choices of coordinates. We will describe in some example that will be good enough for us how this dependence on choices of coordinates affects these actual functions, and that will then be used in the description of well, this modular functor, the game of changing the gluing patterns in the construction of the conformal blocks next time. That is Wednesday. So stop here. Thanks for your attention.
If there are questions.
One, in the in the case of the blocks on the sphere with 3 points, the starting building block, you have your one identities. I was expecting a further term with kind of Schwarzian type additional term.
Thank you. That's indeed bringing me to make some remark that may be useful also more generally. So we have used special coordinates with special transition functions. What is glued from the transition functions, well, this was basically what was in the gluing. These are of Möbius transformation type. Gluing such coordinates defines what is called a projective structure. So implicitly, indeed, the construction that I've presented here depends not just on a complex structure, but on a choice of the projective structure. And this is a way to say, maybe in more professional terms, what we see here. If we fix the projective, transformations that fix a projective structure, these are Möbius transformations, and they're characterized by the property that the quotient vanishes. They won't change energy momentum tensor expectation values. But whatever changes the projective structure will therefore change here the energy momentum tensor expectation values. So they do depend on the choice of projective structure on top of the given complex structure defined by, say, net function. Section, okay, also next time I will, yes, of course, you know very well. These are sections of some projective line bundles or vector bundles, and how precisely this works, I want to say next time. Other questions?
Questions? So let's thank you again. So I would propose we come back at 11:30. We take 20 minutes of coffee break on the cathedral.
Oh, this one. Oh, they have CFT. Yeah, yeah. This is different type of text.
Variation is scaling.
In what sense?
Yeah. So as described before as lattice model.
I see. So you cannot just
Next year.
Yeah.
Then, you just